Okay, in this video, we're going to do the other two equations that I told you we were going to do. One deals with the Rydberg constant and a transition of an electron. And the last one deals with de Bruglie's wave equation relating wavelength to mass. But we'll get to that second one in a little bit. Let's talk about this one. Sometimes electrons get excited. And when electrons get excited, they go up to a higher level. Like an electron, for example, is supposed to be maybe on the first level or first shell, and then it got excited and it went up to a higher level. When that electron falls back down to the level it's supposed to go to, light is emitted, okay? Radiation, something comes out. So this over here deals with the amount of energy that is released when an electron goes from a higher level where it wasn't supposed to be back down to a lower level. Okay, so this equation here is energy is equal to h nu. That's the same as the one we saw in the previous video, but then the new part is this. This is the Rydberg constant. Remember, this is Planck's constant. We already saw that. This is the Rydberg constant. Rydberg constant is 2.18 times 10 to the minus 18 joules. Okay? Now, this equation is 1 over nf squared. This is final shell level. Final level. Remember how I told you the electron got excited. It's at a higher level, and then it's falling back. When it falls back down, that where it fell is the final. Where it started off is the initial, where way up there, wherever it was. So 1f squared minus 1 over ni squared. So 1 over nf squared minus 1 over n. What is the f and what is the I? F is final and I is initial. Okay, so hopefully this will become clearer once we actually go ahead and do a problem with it. Again, it's pretty straightforward, plug and chug. All right, calculate, and you'll be given the Rydberg constant, all right? Calculate the energy of a photon of light emitted from a hydrogen atom when an electron falls from level n equals 3 to level n equals 1. So again, just from the wording, n equals 3, that is the initial. N equals 1, that's the final. That's where it ends up. All right? So now we plug everything in. We're going to write energy is equal to Rydberg constant. We don't need this because they don't want us to find nu. The cool thing about this is that we could be asked to find nu, or we could be asked to find lambda based on the relationship that this is energy and this is energy also. Okay, so that means this can equal this. Energy is equal to Rydberg constant, which is 2.18 times 10 to the minus 18 joules. And then we go 1 over, now what is final? This was initial and this is final. So 1 over 1 squared minus 1 over 3 squared. Okay? Plug it into your calculator. Obviously, do this first. Press equals and then multiply by this, and you should get the answer of 1.94 times 10 to the minus 18 joules. Okay? Why is it joules? Because energy is joules, and there are no units over here. This is joules, so that means this has to be joules. Okay? That's easy enough. Now let's do the same type of problem, but kick it up a notch. So instead of wanting energy, we're going to be asked to find wavelength. All right, so let me erase this and give you our second problem here for this. Okay. All right, what is the wavelength? And then how do you know you're supposed to use this equation? Well, anytime they talk about an electron going from one level to another, this is the equation you're going to use, because an initial to a final, you're going to use this equation. Okay, so what is the wavelength of the light emitted when the electron in a hydrogen atom undergoes, and the buzzword a lot of times is transition. So transition meaning is going from one level to another. Undergoes transition from energy level n equals 6 to n equals 3. So n equals 6 is the initial, n equals 3, that's where it ends up. Okay? So energy is equal to h nu is equal to Rydberg constant, 1 over nf squared minus 1 over ni squared. All right. So we know that in order to find lambda, remember nu is equal to c over lambda. Okay? So instead of putting nu here, let's put c over lambda. So we have H, we have C, we have RH, we have NF, we have NI. We have everything except for lambda. So we plug everything in. Let's go ahead and plug everything in, guys. So 6.63 times 10 to the minus 34 joule second, because that's the H. C is 3 times 10 to the 8th meters per second. Lambda is in the denominator. Remember, you can't leave an unknown in the denominator, so you're going to have to manipulate the equation and make sure that your lambda is in a numerator somewhere and everything else is on the other side. Again, I'm not here to teach you algebra and manipulation. I know you guys can handle that on your own. Okay? However, if you are having difficulty, make sure you come and talk to me and I'll be happy to do it with you. All right, so we're good with this side. Now let's make sure we have this side here. So 2.18, looks like I'm going to get stuck. There's not a lot of room, times 10 to the minus 18. That's the Rydberg constant. And then final is 3. So 1 over 3 squared minus initial is 6, 1 over 6 squared. Hopefully you can see all that. Okay? So we plugged everything where it's supposed to go. Now you need to pick up your calculator, solve this side, bring this down here, bring lambda over here, do the full division properly, putting parentheses so that you don't end up getting weird answers. When you do it correctly, your final answer is going to be lambda is equal to 1.09 times 10 to the minus 6. What units do we have? It's got to be meters, because everything cancels and you end up with your meters. So this is meters. What if they wanted it in nanometers or angstroms? Again, you can do the conversion. If they want angstroms, it's 1 angstrom is 10 to the minus 10 meters. If they want nanometers, it's 1 nanometer is 1 nanometer is 10 to the minus 9 meters. Okay. So anyway, you know how to do that conversion. Good. All right. So that's that. And then let's go ahead and do the final one, which is de Bruglie's equation. It's kind of cool because de Bruglie was this PhD student who Einstein said, yep, give him a PhD, even though he wrote a dissertation that was only like 25 pages long. Most dissertations are several hundred pages. I think mine was about 200. My husband's was maybe 300 pages long. But obviously it's not the quantity, it's the quality. And de Bruglie got it with just 25 pages. But the cool thing about the de Bruglie equation is that he was the first one that related the mass and the wavelength. He related mass to wavelength. So basically, if you know the mass of anything and the speed, you can figure out its wavelength. You can even figure out your wavelength. If you're running really fast, you know your mass, you know your speed, you can figure out your wavelength. It's going to be a ridiculously small wavelength, and totally insignificant, but you could do it. Okay, so this is the de Bruglie equation. And that is lambda, wavelength, is equal to h, which is Planck's constant, over mv. So h is a joule second. Mass is in kilograms. Velocity is in meters per second. Okay, and lambda obviously is in meters. So how is it that everything cancels, guys? Do you remember back in chapter 6 when we talked about what joules is? Kilograms, meters squared, per second squared. So if you plug this in instead of joules, everything cancels and you end up with just meters. All right? Okay, so plug and chug. If you have h, you know h because that is a constant. And you know the mass, but it has to be in kilograms. And you know the velocity in meters per second. You can figure out the wavelength. All right, so here is our problem. What is the wavelength of an electron traveling at 1/100th the speed of light? All right. Wavelength traveling at 1/100th the speed of light. So we have to look up, there's a wavelength, put this here, 6.63 times 10 to the minus 34 joules second. The 1/100th speed of light is 3.00 times 10 to the 8th, and you have to divide that by 100 to get the speed of that electron. The mass of an electron, don't know why I don't have it in my notes here, but I just go to the back of the book and it's got a whole bunch of things here. It says mass of an electron in kilogram is 9.1093829 times 10 to the minus 31 kilograms. I'm just going to stick to, I would say 3 sig figs. So I will go 9.11 times 10 to the minus 31 kilograms. So 9.11 times 10 to the minus 31 kilograms. Be careful with these types of problems because you may be given, let's say, a baseball or a kid or something. You may be given, but the mass not in kilograms. So always convert your mass to kilograms, okay? Make sure that your velocity is in meters per second. If they give it to you, let's say in, I don't know, feet per minute or some ridiculous thing like that, just always convert to meters per second, because that way all your units will cancel and then you'll end up with meters. Remember, this comes here instead of joules, then your kilograms cancels, meters cancel, seconds cancel, and then you end up with just a meters by itself. Okay? Let's plug in these numbers and see what we have. Let's see. Okay, 6.63 times 10 caret minus 34 divided by, I'm going to open up parentheses, 9.11 times 10 caret minus 31, close parentheses. Okay, and then I'm going to press divide again, open parentheses. If this is divided by 100, so I'm going to move it 2 places. So divided by, why can't I think? All right, so divide by 0.03, right, times 10 caret 8, close parentheses, equals. All right, so I have, clutter here. I have 2.43 times 10 to the minus 10. Okay, so 2.43 times 10 to the minus 10 meters. Okay, and what if I am asked, where is that on the spectrum? If I went ahead and did the conversion to nanometers, it would be 0.243 nanometers, but let's see here, times 10 to the minus 10. It looks like it's in the X-ray zone. If you look at the electromagnetic spectrum, wavelength, the section that has it right over here, it says 10 to the minus 10. Anything that's around 10 to the minus 10 is in the X-ray zone. Okay, good. So now you know how to do that. And you learned all 4 equations for this chapter.